Hello boys and girls, welcome to another episode of FoulkesBrau. I thought today we'd do another back to basics video, still concentrating on transistors. Last time we looked at using a transistor, a bipolar junction transistor, as a switch. In other words, we were using it in the saturation region, which is fairly simple. Today I thought let's have a look at it in the active region. Let's see how we can do something useful with a transistor. I'll link the previous video in down below at the end. Let's jump on the bench and let's have a look. Alright, so here we are. So in the previous video we looked at using a transistor as a switch. In other words, we were looking at in the saturation region, we were turning the transistor on hard and basically using it as a switch. Of course, there are things to take into account when you're dealing with high frequencies. There's different circuits we can put because the transistor base does store charge, and as we know, charge is what goes into a capacitor, and it has to discharge somewhere for it to switch off. But what happens if we use a transistor in the active region? In other words, let's say we need to make a voltage regulator for some or other reason and we don't have whatever voltage regulator on hand. Well, we can actually use a transistor to do that. I'm going to do two circuit variants today on it, and we'll breadboard them and have a look. Basically what we're going to do is we're going to use in the first circuit a series emitter follower circuit for the transistor to act as a voltage regulator. So let's draw the circuit here. So we're going to come to our BJT. Again, the emitter is on the downside. We're going to come down from the base, and what happens if we put a funny looking thing like this in? A Zener diode will go out from our transistor and we'll just drive an LED like that. And of course we need something to switch our transistor on, and I will put a resistor in here like that, and we're going to supply this with 10 volts, something simple like that. I hope you can see it. So we have a resistor, we have our transistor, we have a Zener diode, and we have an LED with a current limiting resistor. So let us say this specific circuit that I want to drive, I'm going to use a 2N3904 for the transistor. I only have at the moment 10 volt Zeners, so we'll call that VZ. It's 10 volts. From the data sheet, IZ is 5 milliamp. The LEDs I have are bright whites, so they've got 3 volts, so we call it VLED. It's 3 volts. iLED, let's say 20 milliamp that we want to drive. So we have this base resistor that we need to take care of, because we're not going to switch the transistor on hard, and you'll see that in a minute. I said we're going to supply with 12 volts, sorry, not 10. The Zener is 10 volts, and that is obviously ground or 0 volts. Well, this is pretty easy to calculate. First thing we need to do is look at the data sheet for the 2N3904. Like I say, we're not going to use it in saturation. We're going to use it in the active region. And if we look at the 2N3904 data sheet and we look at the on characteristics, the DC current gain, we know that the minimum gain for the current at the collector at 10 milliamps is 100. The gain for the current at the collector of 50 milliamp is 60. So we want 20 milliamps, so we can take a gain roughly of 80. So I'm going to say my HFE or beta is 80. We know that we need 5 milliamp through the Zener. We now need to know what current do we need on the base of the transistor, and that's pretty simple. If we want 20 milliamps, if we take the 20 milliamp, so let's say I to the B, or I over the base equals 20 milliamp divided by 80, and that should give us, if I do the maths here, 20 milliamp divided by 80 is 250 microamp. 250 microamp, not much, plus our 5 milliamp, so we've got 5.25 milliamp that must flow through R1, we'll call IR1, to 5.25 milliamp. Not very much, is it? Well, to calculate that is actually easy. We take the supply voltage less the Zener voltage and we divide it by the current. So we can say Vs minus Vz over the 5.25 milliamp, which is 12 minus 10 over 5.25, which is 2 over 5.25, and if I do that, 2 divided by 5.25 milliamp, we get a resistor value of 380 ohms. Very simple. So we'll make that resistor 380, and that should serve our transistor fine. To calculate this, we just subtract the 12 from the 3 required by the LED, which will give us 9 divided by 20 milliamp will give us about 400 and something ohm. So just to keep it easy, I'm just going to make that 380 ohm as well. Simple. How does this circuit work? Well, let me restart the clip and I will show you. So how does this circuit work? It's actually very simple. As we start, forget about this part down here. The transistor is off because there's nothing on the base. So as current starts to flow through that resistor, it will start to flow into the base of the transistor, as well as to the Zener. But if the voltage is too low, the Zener current won't flow, so the voltage will build up here. The difference between the base and emitter will cause the transistor to switch on as long as it gets above a certain point. So now the transistor starts switching on, we have current flowing this way, and obviously we get voltage. What happens when the voltage goes too much? Because now we're trying to control the voltage here at our Zener voltage, which is 10 volts. If the voltage goes above 10 volts here, the base emitter voltage will grow, causing this transistor to switch off a bit, because now that gap has become less than what we need to actually conduct. The excess, obviously, because the input voltage would be rising as well, will start to conduct through the Zener. The Zener will strive to keep that voltage there at 10 volts. So very simple. The voltage rises here, the base emitter voltage decreases, the transistor starts conducting less. It doesn't switch off, it conducts less. As the voltage decreases here, the gap is more, we start conducting more to bring that voltage up. So very crude, but it does work. I wouldn't use it for something critical. It does have its downsides. Downsides of this common or emitter follower, typically it hasn't got good regulation for high current. So if you have a high current demand, well, then you don't really want to use this. The other problem is it's got a very high power dissipation. In other words, we are losing heat in the form of current flow. Obviously this device will heat up, the same with that resistor. So we're losing heat in these devices. So very poor efficiency and a really high power dissipation. So there is another way to skin this cat. We'll do both circuits. I'll just draw them first. So what happens if we did this? Same thing, transistor, NPN, to our base. But what I'm going to do, I'm going to put another transistor in here, also NPN. Then we'll go to our Zener, to our ground. And what I'm going to do is I'm going to do a little trick here. I should have made that longer. We'll put a pot in there, and again we'll come to our LED as a load. Looks similar, not too different. The only thing that we've got now is this transistor here. And what we're doing with that is we actually creating a bit of feedback into the system. And you will hear engineers talking about feedback and negative feedback and things like this, and how it's always good. This will give you a better control over your voltage, less power dissipation and things like that. It's a better efficiency. The calculation for calculating that resistor is exactly the same as what we did for the LED. This pot, I'm just putting a 1K 1 turn in, nothing fancy. The Zener will stay the same, so the same things apply. Again, how does it work? Very similar to the first one. It works off this base emitter voltage. So when we start, the transistors are dead. We build up. Obviously this transistor is off. We get voltage to here, which will be higher than the emitter. This transistor will switch on. And as we go, as this voltage builds up, this voltage through this pot, which we can set, and it's got a few things that we can do with it. So we're going to set this voltage to here. This voltage will eventually be bigger than this voltage, so this transistor will switch on, adding a little bit or proportion of our output voltage to this that will now sit on the Zener. Now as the voltage goes up again, this emitter voltage will start closing the gap between the emitter and the base. This transistor will start switching off. As this transistor starts switching off, this voltage will start dropping, so will this transistor starts adding less feedback, so we'll eventually get to the diode not conducting and just keeping the voltage. Again, this will give you, because we're adding the feedback, remember the transistors are acting in the active region, they're not on or off, they're conducting more or less. So this transistor is adding feedback from the output, adding a proportion of the output voltage back into the circuit to help this transistor. Nothing very fancy, but it works like a charm. Now, why would you do this? Well, it's good to understand the building bricks or the basic blocks of what we're doing. So when you come across circuits where you don't have schematics or things like that, and there's funny things in, or there's something in, you know what you are looking at, and you can quickly determine whether your fault lies in that part of the circuit or not. So, two very simple circuits. In modern day solid state packages like your LM7805 and those sort of things, this is a discrete package, and this feedback is actually achieved through a differential amplifier. So you could actually replace this. You would have your Zener as your reference on one side, and you would have your feedback as the part to add into the circuit. So very simple. Let's get on the breadboard and let's have a look. So here on the breadboard we have our two circuits. Let me try and get the zoom to work. No, I don't want focus, I want zoom. Okay. Okay, there we go. Much better. So on the left we have our single transistor solution with a 10 volt Zener there at the back, our two 380 ohm resistors, and our LED power to the collector of the circuit. If we just try and slide this underneath so you can see the circuit that I'm looking at. So let's just zoom out a little bit, like that. So there we go. That is our circuit. You can see on the left. So the red wire over here is that going from the positive rail to the collector over there. And that's about it. The resistor goes from the positive rail to the base. The base is also connected to the 10 volt Zener, and the Zener is connected to the 0 volt. And then we just have on the emitter side our LED with its current emitting resistor. On the right we have our dual transistor setup with its pot. So basically we have our two transistors, the feedback being that transistor with that pot, and then it goes into the base of the second transistor. So across the output we take a piece back into the base of that transistor to switch it on more or less, to add more or less feedback for the Zener. Again, same thing that we're doing on the other side. So let us get our multimeter out and let us take some measurements, because measurements are the thing that counts. So what I'm going to do, I'm just going to switch my power supply off, well, the voltage all the way down, and what we will measure is the output over here of the voltage regulator, in other words the output that's driving the LED. So if I switch my output on, we are at 0 volts, 1 volt, 2 volt, 3 volt, 4 volt, and the LEDs just switch on, 5 volt, 6 volt. You can see I'm 1 volt down on the output, 7, 8, 1.3 volts down, 9, 10, 11, 12. So we're a little bit down, and that's to be expected, losses on the breadboard and things like that. If I measure the Zener voltage, which will be on the base, we can see our Zener is at 10 volts. But we are at 9.38 on our 12 volts. Remember, we wanted 10 volts out, so we're 0.7 out. If we move to the output of the second circuit, we are 9.4 volts. So I just want to get this. And what I'm going to do is adjust this pot. I'm going to add more feedback. If I can get in around this. Oh, just too much. Ah, that's good enough for me, for South Africa. So what you can see is by adjusting the pot, I can adjust the amount of feedback to add. So that I can get the precise voltage that I want out. So a very neat little circuit to have. How about if we have a look on the oscilloscope, what this is doing. So let me get the oscilloscope probe in, and then we'll move up and have a look. Let's just put this on the negative rail. We'll just go with that. Zener over there. Now that's Zener over there. And we want the output over there. Have I got this on? No, it doesn't look like it. Let's find a 0 volt. There's one. Okay, I'll lift you up so that you can see what I'm seeing on the oscilloscope. Right, so there we have what I'm measuring here is the base. In other words, the voltage that will be telling the transistor, the base voltage, to switch on more or less. And hopefully what you can see is I'm measuring this at 20 volt, 20 millivolt per division, and I'm reading roughly about 30 millivolts peak to peak. But what you should be able to see in there is the slight variation, the slight fluctuations. And let's see if I make the intensity less. There you can sort of see, you can see it's going up and down. Not much, obviously, but that's telling the transistor give me more volt. In other words, the output is telling it, give me more voltage, less voltage, more voltage, less voltage. Of course, these circuits are very temperature dependent. Now I'm going to go to the base of the second of the double transistor, or the circuit with the feedback, and you can see same sort of thing, just the amplitude of the base, where am I going? The amplitude of the base voltage is more. Okay, so let's see if I do it like that. Will it help? No. So you can see that snaky sort of thing going on in there. Let us go and look at, we'll just set this down, the output. We'll go to the first circuit. You can see we had 5 volts of division. Obviously we can't have volts peak to peak, but what we can have Vmax 9.6 volts. If we look at the second circuit, again our Vmax is 9.6, but obviously we need, I've messed around with this pot and stuff. So 2 circuits you can build very relatively simply, very cheaply. I mean, 2N3904 costs you a couple of cents, the resistors a couple of cents. Really not much to it. Maybe a pot is a few rand versus a couple of rand for a regulator. The thing to remember that these circuits are temperature dependent. Xenodiodes are notorious for it, and so are resistors. So as the temperature goes up, this thing will go out of whack. So I would use the differential type amplifier that we've used the second circuit, and then you know you're a bit more stable. So let's finish up. There you have it. We've come to the end of another episode. I hope I've given you some ideas. If you've run out of a regulator and you need to improvise one, well, now you know how to do it. Just a word of warning, they are temperature sensitive, so you can get into problems where you have fluctuations of temperature. But yeah, you can see we can do many things with transistors. It's really up to you. Anyway, till the next time, take care, be safe. Cheers.